So here we talk about invertibility. So definition. For T in a map from V to W, T is called invertible if there exists some S in, this time it's a map that sends elements in W to vectors in V, such that TS, so can you tell me what's the domain and range of TS? Where does it go from where to where?
W to W.
W to W, right? So S takes elements in W, sends it to V, but then you apply T and you get another vector in W, right? So this is a linear map from W to W, but let's say this happens to be an identity on W, okay? And ST, okay, ST is a map from where to where?
V to V.
V to V, so this will be an identity from V to V, so this will be an identity on V. If you have such an S, then you call T as invertible, right? Okay. So I guess we need to think of some examples. So for example, let's say T is from R2 to R2 such that X, Y is sent to X comma X plus Y. Okay. Now I claim that this is an invertible map. In other words, I have to find some matrix, some linear map that would undo this thing. So, for example, 1, 1 is sent to 1, 2, right? So I need something else that sends 1, 2 to 1, 1. What else? 1, 0 is sent to 1, 1. So 1, 1 has to be sent to 1, 0. Where is 0, 1 sent to? 0, 1 is sent to? 0, 1. So 0, 1 shouldn't change. Okay, so can you think of such a map? So think of a map where it's going to undo this. Well, think of it this way. That's what we want, right? So let's ask this question. What is S? Well, this is what we want. So now let T as X plus Y. So that Y is equal to X, no, T minus X. Right? Let's see what that does. That will make S of X comma T equal to X comma T minus X. Okay? So let's see if that does what we thought it would do. What happens if I plug in 1, 2? Takes 2, 1, 1. Oh, that's good, right? How about 0, 1? 0, 1 is sent to 0, 1. So it looks like this whatever this did, applying S will undo it. Do you agree? Okay. So that was our thinking phase. So the solution would be, let S of xy equal to x comma y minus x. Okay, and do you see that instead of using t, I went back to y? So I just replaced t by y. Then, ts xy is going to be t of x comma y minus x. But then I'm plugging this into this formula, which is x comma x plus y minus x, which is x comma y. So look, I went from x comma y to x comma y. What is that? Identity function. Okay, so we do see that TS is identity. Okay. What about reverse? ST xy. Well, txy is x comma x plus y, right? Now we plug this into this formula here, so that x is x, so that's okay. But then x plus y becomes y, so x plus y goes into y, subtract x, and again, this is x comma y, so that tells you that ST is equal to identity as well. Okay. Now there's still another way to obtain the same thing. I wanted to show you a solution that doesn't make use of matrices because it makes you to think more. But if you use matrices, this is even simpler. What's the matrix of T using standard basis? Well, this is like 1, 0 and 1, 1, right? So this will become 1, 0, 1, 1. And because I need S to be the inverse of this, the matrix of S must be the inverse of this guy, right? So let's think about 1, 0, 1, 1 inverse. Well, we all know the inverse formula is 1 over 1 times 1 minus 1 times 0. You switch these two, and then you negate this. Right? And this is just 1, so this is just 1, 0, negative 1, 1. Oh, what kind of map does this? Well, it must be xy that gets sent to x comma negative 1 times x plus y, right? Because the values are 1, 0, negative 1, 1, right? 1, 0, negative 1, 1. That's exactly this map, okay? So we were able to come up with this map by just some observations and thinking, but you can get the same result just by inverting a matrix. And by the way, when the map becomes more complicated, then this will be the way to go. Because like trying to do it this way will be very hard, right? Okay, but anyways, such is an example of an invertible map, okay? What we have not shown is that such S need not be unique, right? There is no assumption that there should exist a unique S, right? But it turns out that if such an S exists, it has to be unique, okay? So let's try to prove that. So 3.54 says inverse is unique. Okay. And to prove that, let's suppose S1, S2 are both inverses of T. And to show uniqueness, I have to show that S1 is same as S2, right? So I'm going to say S1 equals to S1 times identity. Let's see. For this to make sense, this identity should be on V or W. Which one? W, right? So S works on domain of S is W, so I need IW. Okay. But if you have identity times a linear map, it's always same as itself. So you can always write down S1 as S1 IW. But now I'm going to write this as S1 T S2, because TS2 will be same as IW, right? So I can rewrite IW as TS2. And then we use a property that we proved some time ago, which is that when it comes to composition of linear maps or multiplication of linear maps, then associativity holds. So S1T S2 is same as, S1 of times TS2, parenthesis this way is same as parenthesis grouping the first two and then S2. Well, if you have S and T, then this is same as IV, right? Identity on V, so you end up with identity on V as 2. But what's that? That's just S2, right? Yeah, identity doesn't do anything, so multiplying an identity to a linear map doesn't change it, so you just get that, okay? So this shows that S1 is equal to S2, thus showing uniqueness, okay? And therefore, we will denote by T negative 1 this unique inverse. Okay? On the face of it, this is a very simple looking theorem. It says that something's invertible if it's both injective and surjective. And if you took a basic proof theory course, it's not unprecedented. You've seen something similar, which is that a map is bijective, right? If it's injective and surjective by definition, but we also know that a function has an inverse if it's both injective and surjective, right? That's something that you learn how to prove in basic proof theory. So you might think this is not so different. However, there's a small part where you have to be a bit more careful than just that. So let's see how this thing goes. So let's, again, this is if and only if, so we have to prove in 2 steps. Let's prove this. So if T is invertible, I want to show that it's injective and surjective. Well, first, injective. If T of U is equal to T of V, to show injectivity, we have to show that U and V are equal, right? But it says it's invertible, so T inverse can be applied both sides. And because by definition of being an inverse, the composition becomes an identity. And what does identity mean? It means that you just get back whatever you plugged in. So identity applied to U is just U, identity applied to V is just V, okay? So that's what you get. Now I spell this out, but you know, when you have to do something like this in homework or during the exam, you don't have to spell it out that much. You can just say, these are inverses, they cancel, so that gives you U equals to V. So that's all you have to write down, okay? All right. that's the proof of injectivity. How about surjective? For surjective, for any W in W, I have to show that there's a V where T of V is equal to W, right? So, let V is equal to T inverse of W. Since the inverse will map something in W to V, right? You can do such a thing. Then T of V is T of T inverse of W, and again they cancel and then you get W. Okay. So that shows that W is in the range of T. Since range of T is a subspace of W, then this being inside here, that inclusion is obvious, but now we've seen that anything in W is in range of T, so that shows that range of T is equal to W, and that's how you prove surjectivity. Okay? Now let's prove the opposite. If T is both injective and surjective, then it's invertible. Okay? So how do you do that? So for any W in W, okay, since range of T is same as W because of surjectivity, okay? There is a V in V such that T of V is equal to W. Okay. Define a function from W to V so that if TV is W, then S of W is V. Okay. This argument above shows that for any W in W, you have such a V, right? Okay. So where V is as defined above, okay? How do you know that this is well defined? For S to be a function, you need this pairing, W to V, to be well defined. How do you know that's well defined?
Should be injectivity.
Injectivity, right? So, if S W is V1 and SW equals to V2, then T of V1 is W and T of V2 is W as well, because you switch these around, that's what it means. But by injectivity, T is injective So V1 is equal to V2. So this shows that you can't have different outcomes for the same input W. So thus S is well defined. Okay. So if this was merely showing that a function is invertible if it's both injective and surjective, this is all you have to write. However, when we are here, we have to show something more. Who can tell me what else we need to show? It's a bit hard to think, but see, in our definition of invertibility, such S also has to be in the linear map from W to V, right? S has to be from here. But S is just a function. We don't know if it's linear or not. Okay? So we still haven't completed the proof because we have to show that S is linear. Okay? Alright. So let's prove that. We still need to show that S is linear. Okay. So let's see. If S of W1 is V1 and S of W2 is V2, right? Then T of V1 is W1 and T of V2 is W2 by the definition. And because T is a linear map, the additivity is like this. T of V1 plus V2 is W1 plus W2. Right. This is by additivity. Well, it's really, additivity says T of V1 plus T of V2, right? But that's equals to W1 plus W2 because of this, right? So additivity shows that, but then whatever relationship you get from T, you just switch input and output. That's your inverse function S, right? So S of W1 plus W2 is now going to be V1 plus V2, but what's that? That is S of W1 plus S of W2. Okay? So that shows that additivity holds for any W1 and W2. If S of W is V, then T of V is W, and T of lambda times V is going to be equal to lambda times TV, which is lambda times W. Take the same inverse, so this is your input, that's your output, so that says S of lambda W is equal to lambda V, but V is SW, that's what we know, so that's going to be lambda times SW. So we're done. These two arguments show additivity and homogeneity, and therefore S is really in WV, and TS is identity, and then ST is identity as well. So these two are easy to be checked, just straightforward from the way we made the map. Okay. The title of this section was Invertibility and Isomorphism of Vector Spaces. So in 3.58 comes the definition that says an invertible map, invertible linear map is called an isomorphism. Okay, and if you take abstract algebra course, then there's several kinds of isomorphism. There's the isomorphism between groups, there's the isomorphism between rings and fields and so on and so on. So whenever you say isomorphism, it's like it's a bijection between two things that preserve the structure. Okay, so in a wider view, this is really saying it's isomorphism between vector spaces. Okay, so that's what we mean. But in this class, the only kind of structure that we're interested in is the vector space. So when you say isomorphism, what else can it be? It means isomorphism of vector spaces. And if there exists an isomorphism between V and W, two vector spaces, we say V and W are isomorphic. Okay. And again, we just say isomorphic here because we only have vector spaces, but in a bigger picture, if you're talking about something similar in abstract algebra, you have to specify isomorphic as what? You have to say it's isomorphic as vector spaces. Okay? And then 3.59 has an interesting theorem which says that V and W are isomorphic. Now, notice that there is no symbol for isomorphism in the textbook, but we'll just use that as the isomorphism. Okay, so we'll say V and W are isomorphic as vector spaces if and only if dimension of V is equal to dimension of W. Let's prove this. Proof. Okay, for the proof going this way, we are going to assume that V and W are isomorphic, which means there exists an isomorphism between V and W. So let T be an isomorphism between V and W. Okay, so let's say that. And since it's talking about dimensions, we can use that fundamental theorem of linear maps, right? So what was that theorem? It says dimension of V is equal to dimension of the null space of T plus the dimension of the range of T. Okay. But we also know two things. T is injective, means null space of T is, we learned this last time?
0.
0, yes. And T is surjective, means the range is what? W, the entire thing W. So we use that, and of course, what's the dimension of the null space? The
0.
Yeah, trivial space is 0. So this is just going to be 0, and we have dimension of V equal to 0 plus dimension of W. Oh, so it's a direct consequence of the fundamental theorem of linear maps. See, no wonder it's called the fundamental theorem of linear maps, because it has so many consequences, right? Okay, now let's prove the opposite direction, which is saying that if dimension of V and dimension of W are equal, there's an isomorphism between the two. Well, if I say let n be the dimension of V and W, because we're assuming that the dimensions are the same, we have some n where dimension of V is the same as dimension of W. So that means there exists some V1 through Vn, a basis of V, and W1 through Wn, a basis of W. Okay. Now construct a T such that T of C1 V1 C n Vn is equal to C1 W1 plus da 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 C n Wn. Okay? Now we can directly go from here and just show that this is a well-defined map, which is both injective and surjective. But you know, I think we can just do this. What is matrix of T? Let's call this B1 and B2. B1, B2. What will this be? Well, what's T of V1? To just get V1, you need what? 1 and then 0, 0 everywhere. Okay. If you plug in 1 and 0 everywhere, what do you get on the right side?
W1.
Just W1. So T of V1 is W1, T of V2 is W2, and so on and so on. If you write those equations down and write down the matrix, what do you get?
Just the diagonal, 1, 0, yeah.
Right? So now you just say, let S be a linear map from W to V, so that matrix of S B2 to B1 is just a diagonal. Okay. Then of course, if you multiply these two, you get the identity on V, because it's B1 to B1. Right? And it's, both ways it's identity, so you see that T is invertible and we're done. Okay. So that's like one strategy. Like if this is too vague and you don't like it, then another way to say is that, well, first of all, why is this well defined? This is well defined because for any V in V, there's a unique representation because V1 through Vn is the basis, okay? And once you have a unique representation, then the right side is just unique, right? So this is well defined. Because for any V in V, V equals to C1, V1, da da da, Cn, Vn has a unique representation. Okay. So what you can say is now S of A1W1 da 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 ANWN as A1V1 da 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 ANVN. Okay. Again, this is well defined, right? Okay. This is well defined for the same reason. Now, one thing that still concerns me a little bit is that I haven't shown why this is a linear map. But, you know, check that indeed ST is an identity and TS is also an identity. Okay. So we don't really have to go through linear maps. If you have an invertible function, then it's always bijective. Oh. Okay, we still need to show linearity. All right. Sorry, I forgot that to be an isomorphism, you can't just have a bijection, it has to be linear. So you still have to show linearity. It's cumbersome to write down. You just have to write two. Let's say C1 through Cn is one vector V, and then another U is like D1 through Dn, and then just apply, check that it satisfies the additivity and homogeneity. So check additivity and homogeneity. Okay. That part I'll just leave it to you. Okay. You know, the book also just skips several proofs, so I think I can skip something like this one. It's just like a lot more writing. Okay. So once that's done, then now you've found an invertible. You have an inverse, so you have an invertible linear map between V and W, so you're done. Okay. So that part is proved. So that's what it is. Okay. So that says if you have two vector spaces that are isomorphic, then they must have the same dimension. Now, this can now be used to talk about the comment that I said earlier, that this is a vector space, this is a vector space, and then these are isomorphic because there's this map, matrix map, which takes a linear map to a matrix, right? Here I just want to show that this is both injective and surjective. Okay? Why is this injective? Well, if a matrix representation of a map here is the zero element, which means zero everywhere, okay, then by definition it says T of V1 through T of Vn would be equal to 0 times W1 plus da 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 0 times Wm, 0 times W1 through 0 times Wm. And if that's true, then we see that T is just 0. Right? So we see that the null space of T is just a single element 0. Okay? That shows that T, this M is injective. This shows that null space of M is just 0, where 0 is the 0 element in here. So that's injective. To show surjectivity, then you can just construct a map. So if you have anything in here that's AJK as a matrix, then you again construct something like this. And once you have that, then you just show that just having these set of equations will uniquely determine the T. So that part just has to be done separately. So, so surjectivity is left to you as well. Left to the reader. Okay, so that shows that there's a isomorphism between the two, and the direct outcome is 3.61, that the dimension of this space is equal to the dimension of V times dimension of W. Because we assume that dimension of V is n and dimension of W is m, and if you have f m n, this one, what's the dimension of f m n? We already said that this is m times n, right? So this 3.61 is a direct consequence of showing that this m is an isomorphism. All right, so this next part is, again, just a different notation for something that we reviewed earlier in the semester. It's called the coordinate matrix of a vector, right? So if you have the basis B as V1 through Vn, then the M of V, B, and you know, again, this basis B will sometimes be suppressed if it's obvious from the context, or if you want to keep it in general, you just suppress this. This is like a matrix from A1 through AN, where V is equal to A1 V1 plus da 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 AN Vn. See, because V is a vector in V, and V1 through Vn is a basis, for any V, it has to be representable uniquely as a linear combination of V1 through Vn, right? And once you have that, then this is what we used to call as the coordinate matrix, right? The way we wrote this down was V with B. That's how we wrote it. Yeah. But in the textbook, this is how it's written. Okay. Okay. So an obvious consequence of that is the following. If you have matrix of T, so let's say matrix of T is equal to A11 through A M1 and then A1n, then AMN. So if I want the kth column vector, this kth column vector, okay, so tell me what's at the top. What's the first element of the kth column vector? A what? A
1k.
1k, good. And the last one is A mk, right? So this one, which is denoted as dot comma k. K is the column number, so if you do dot comma k, this is the kth column of this matrix. So, here, you really just need to learn how to read these notations. Once you read them, then it's kind of obvious. And then here, I'm really assuming that you have a basis. This is really MT, B1, and B2. Where B1 is the basis, B1 is really V1 through Vn, okay? And B2 is W1 through Wm, the same kind of thing that we did before, okay? And I'm trying to say that if I do T times Vk, well, what is that? Well, T times Vk is really, by definition, it's this one, isn't it? Right? So, what is TV1? That's A11 W1 plus da 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 plus AM1 WM. And A11 through AM1 will give you the very first column, right? So if you go down, if you have T of Vk, the way we build this matrix is by applying Vk to T, applying T to Vk, and rewriting that as a linear combination of W1 through Wm. And the way we write it is as A1k W1 all the way up till AMk Wm. And that's exactly A1k through AMk is exactly the kth column. So this is just by definition true. If you just recall how we got this matrix, this is just true by definition. Okay? Now, if you accept that, then this is kind of natural because, see, the way we think of T of V, if I say V has the, sorry. The way we think of MT times MV, if I think of this as V as, say, A1 through AN, so that's our coordinate matrix, okay? We learned in the previous section that this is same as A1 times MT's the first column plus A2 times this matrix's second column all the way up till AN, the matrix's last column. Right? So that's how we understood it, right? Which is like, what's that? That's A1. Well, MT.1 using this is MTV1, right? Plus A2 MTV2 AN. Sorry, I'm going all over the place. Sorry, I should. So here is this, and then now it's that way, okay? Right. But then look, this M, we already showed that this is linear, right? We already showed that this is linear, so this is same as M of T of A1V1 plus T of A2V2, T of ANVN, which is M of T of A1V1 ANVN. Oh, but what is this? A1V1 through ANVN. That was our V, right? So that's going to be M of TV, and this is proved. So we start from the right side and then we arrive at the left side, so this is true, okay? We denote L V to V as just L of V, and we call T in one of these spaces as an operator. So a linear map is a function between two vector spaces which satisfies the additivity and homogeneity. That's what a linear map is. But if that linear map happens to be a function between the domain and target that's the same, right? In that case, you call that an operator. So an example of an operator will be derivative is an operator on the space of polynomials, right? Because if you take a polynomial and you differentiate it, you get another polynomial, right? So derivative, so let's say, example, d from the space of all polynomials to the space of all polynomials, that takes any polynomial to its derivative, is an operator because the domain and target are the same. Okay. And you can think of several things that are operators. What's an example of something that's not an operator then? Can you think of something?
Something that takes me from like R3 to R2.
R3 to R2, yeah. So is an operator. Example 2, let's say t of x, y, z equals to x plus y and then y plus z is a map from R3 to R2, right? So it's not is not an operator. Okay. And an interesting theorem here is 3.69, which says for t for an operator v, where dimension of v is finite, TFAE. What does that mean? TFAE? Have you seen this? TFAE, acronym for, well, you can think of it later. A, T is invertible. B, T is injective. C, T is surjective. Okay, so what does TFAE mean?
The following.
Huh? The what?
So the following are evident?
Equivalent.
Oh, equivalent.
Yeah, the following are equivalent. Okay, TFAE. Okay, so any one of these mean the other. Okay. Well, the first is easy. If T is invertible, then we already know that it's injective and surjective. We proved that a bit before, right? Okay, so that part is already done. But the strong part is that if you know that T is injective, then you know that it's surjective. If you know that T is surjective, then it's also injective. Okay. And this all has to do with the fact that T goes from V to V and V is finite. So let's prove it. So proof. Well, A implies B already done. So we proved a few moments ago that if something is invertible, then it's both injective and surjective, and vice versa. Okay. Now, B implies C. So let's try to show that. If T is injective, then T is surjective. So how does that work? Well, dimension of V equals the dimension of null space of T plus dimension of range of T. Yeah, again, the fundamental theorem with linear maps, right? Now, if it's injective, we know something here, which, what?
Null dimension.
Nullity is 0, right? The dimension of the nullity is 0, that we know. So we see that dimension of V is equal to dimension of range of T. Okay. But that should mean that V is equal to the range of T, which is saying that T is surjective. Let's see. Is that true? Why is this true? If the dimension of the subspace is same as the entire space, then they must be equal. How do you show that? I have a feeling that we may have already proven this somewhere, but since I can't recall exactly, let's just do this again. So let me write in a different color. So what are we trying to say? Lemma. Let U be a subspace of V. If dimension of U is equal to dimension of V, then U is equal to V. All right. So, we did this before. It's like we show that the linearly independent list of the right length is a basis, and a spanning list of right length is a basis. We show that using that length argument before. So it's definitely done before, but let me just sketch the proof. The way it's proved is like take V1 through Vn of basis for U, right? But then that means V1 through Vn is linearly independent in V of length n, which is same as the dimension of V. And we proved using those arguments before that a linearly independent list of the right length is a basis, right? So V1 of Vn is a basis for V. Okay? But then that means since this is a basis for V, V is equal to span of V1 through Vn, and because this is a basis for U, it's also the span, U is also the span of this, so they're equal. So that's how you prove that. I don't know, maybe it was in some exercises or somewhere, but if the dimension are the same and one is a subspace of the other, then they have to be equal. So that's done. And then you have to show C to A to close the loop. And to show that C to A, you really have to show that if it's surjective, then it's also injective. Because we already have a theorem that says if it's surjective and injective, then it's invertible, right? So we only need to show T is injective. Okay. But that's again proved by dimension of V equals to dimension of null of T plus dimension of range of T. And because T is surjective, this is equal to n. This is equal to n, so dimension of the null T is what? 0, right? So this just says that dimension of null T is 0, but then the only time this is true is if null T is a trivial vector space, right? So this shows B, but B and C together is A, so that's done. So A implies B, B implies C, and C implies A, so any one of those three will imply the other.